name is Adora Sadis, and I'm the project manager for HyperXite.
Hi, my name is Jason Lee. I'm the team captain for FALL18Hyperxite.
I'm Daniela. I'm the assistant project manager.
So a bit about the Hyperloop concept in general. It was first proposed in 2013 by Elon Musk in the Hyperloop Alpha white paper. It has the potential to take you from LA to San Francisco in under 30 minutes, which means that you could live in LA and work in San Francisco, which is pretty amazing. It would be a lot more efficient and sustainable than our current modes of transportation. And it has the potential to be the fifth mode of transportation that we have. A bit about HyperXite as a team. We were first formed in 2015 and attended design weekend in 2016, and we placed fifth for our overall pod design worldwide. The following year we attended the first SpaceX competition where we were one of the top 29 finalists, and later that year we were one of 16 to run in the open air Hyperloop vacuum tube. And this past July we were one of the top 22 finalists to attend the third SpaceX competition. So about our goals and objectives for this year, our goal is to build a high-speed self-propelled pod and complete a safe, successful vacuum run at the fourth SpaceX competition, which is going to take place next summer. And our objectives are to reach a top speed of 250 miles per hour, be vacuum safe, have real-time pod monitoring behavior, and stop safely 100 feet before the end of the tube. And here's a schematic of our pod trajectory. As you can see, we spend most of the time accelerating and then a bit amount of the time braking. Yeah. So overall, just some specifications about our pod. As I mentioned, we're going to be traveling at 250 miles per hour. And here's some information about the acceleration and deceleration. Our pod is going to be 30% lighter than our previous one at 175 kilograms. And the dimensions are going to lead to an overall smaller pod, which means that it should go faster. Okay. We're going to go into more details about each of the different subsystems, but just to give you an idea of how everything fits together, that's the front of our pod, and our braking system is attached to the front. Our propulsion system is right here. We'll go more into detail about that too. Our pneumatics, they actuate our brakes, and here's our coolant. Electronics are placed, batteries are placed in a pressure vessel over here, and then we have our control system. And then our structure is the whole thing, and our stabilization, we have both lateral and vertical stabilization to stabilize our pod. So the progress of our structure, where we're at right now is we have designed a carbon fiber structure with a polyurethane foam core with cutouts to accommodate for mounting different components onto the pod. Right now we're optimizing our design and contacting companies to see if they have any feedback for us and how they can help. And the next step would be to run in-depth simulations to make sure that our design will work. This is a simulation, static structural simulation of our design, and this is a render. So as you can see, it looks like we're in the right track. And here's a cross-section of how the carbon fiber would have a foam core. So a bit more about our fairing. This is an old simulation, but our new fairing is going to be very similar. So one thing that we have to do is run 3D CFD simulations for our new fairing, which will be designed to fit our new pod. So right now we do have it designed, but we still need to optimize it and redesign it to fit more closely to the pod. As our design changes, this design will probably change as well.
So moving on to stabilization. So we have already been able to design lateral and vertical stabilization units. These units are going to be using a zero crush urethane wheel, which is soft but very durable wheel. It is going to allow for some shock absorption. As you can see from this pattern, it allows for some deformations when we do hit SpaceX's track, since there are bumps and irregularities. Right now we're looking into high RPM bearings to work for 250 miles per hour with a 3.5 inch diameter wheel, and that is also vacuum safe. Later on, we're going to also need to do some vibrational analysis as well as some structural simulations for all of these components. Right now, we're doing some preliminary simulations as well. So for our power systems, we're going to be using the same high voltage system as last year, which consists of 9 LiPo batteries, each with 44.4 volts, each in series. It's going to provide around 450 volts and a max operating current of 480 amps to our MREX 228 motor, which is going to be our main source of, or our only source of propulsion. And these batteries are not vacuum safe, so we do need a pressure vessel to contain them. Right now, we're actually looking into getting rid of a pressure vessel and replacing that with clamping these batteries to simulate the atmospheric pressure. That would save a lot of weight and also reduce the size of our pod as well. That is going to be controlled or managed using the Orion battery management system. And afterwards, or later down the line, once we have our system completely set, we'll be doing more rigorous testing of our high voltage system just to prove to SpaceX that we can effectively use these batteries to propel us and also do it safely, which is always a main concern for SpaceX. For controls, we've been able to develop the state machine, which is essentially the top level functionality of our pod and how it's being controlled. We've narrowed down our microcontrollers down to the BeagleBone Black and the Hercules Launchpad. Right now, we're setting up a plan to conduct vacuum testing on these components, since the documentation for these microcontrollers didn't include vacuum safety. So we'll be conducting those tests within the next couple of weeks. We're also looking into speccing out temperature sensors for different components of our pod, our motor controller, batteries. And later down the line, once we have all of the sensors and actuations for our different subsystems, we're going to be developing the final code or software for our microcontroller that we're going to be communicating remotely for our pod. For our braking system, we're going to be using the same Hall-back array as last year. It provides around 2,700 newtons of braking force as well as a 1.5 G deceleration at our max speed of 250 miles per hour. We've already done very thorough magnetic simulations for our assembly to calculate the lift and drag forces for our pod. And we're currently looking into optimizing and reducing the size of our pneumatic system on this braking assembly, just to reduce weight, of course. And we're also going to be optimizing the structure as well, just to make it lighter. Right now it's around 63 kilos. We're going to try and knock that down to around 45 kilos. And also maintain the same minimum factor of safety of 2 that SpaceX requires. So moving on to propulsion, we're going to be using the same MREX 228 motor and in-wheel design that we have been using at the last competition. The only major change for this is that we're going to be using a new motor mount. This motor mount is still going to be able to provide around 5,000 newtons of downforce on the drive wheel, but this time around we're going to be using coilovers to allow for some shock absorption and dampening for our pod moving at 250 miles per hour. Currently, we're trying to redesign this mount just to optimize it, as well as the suspension mount that interfaces with the coilover, and trying to figure out the exact dimensions that we need to get that 5,000 newtons of downforce for the drive wheel. And later on, we're going to be needing to do more thorough testing of our MREX motor, under load as well as without load as well. Once we have our test track built, we'll be able to do more thorough testing on that.
Our cooling system will be used to cool our motor and our motor controller, and we decided to use deionized water as our coolant, which will be stored in a 0.85 gallon reservoir. And currently we're determining the required cooling rate to prevent our motor and motor controller from reaching 60 degrees Celsius, which is its maximum operating temperature. In the future, we'll be optimizing our design and speccing out smaller size reservoirs to reduce the overall weight, in addition to running tests to determine our cooling efficiency. And right here you see an image of a pump and our coolant, reservoir, and then this is our cooling system schematic as well. For pneumatics, we decided to use a Luxfer M060 air tank, and it has a maximum operating test pressure of 5,000 psi. We will be running at around 3,000 psi. And our pneumatic system design includes several safety features to safely and properly actuate our braking system. And we're currently working on optimizing the design again, speccing out smaller tanks to reduce the size. In order to do so, we'll need to determine the smallest size tank possible that can safely and properly actuate our braking system. And right here is a pneumatic braking system schematic. So this diagram shows our team organization. To the right, we have management, which includes myself, Jason, Adora, and our operations manager. Above, we have our technical branch, which includes our subsystem leads and their respective general numbers. Below, we have our non-technical branch, which includes documentation, outreach, lab management, and our safety officer. And to the right, we have our advisors. Professor Rangel is our faculty advisor, and we also have 2 graduate advisors that were former members of the team. And below, we have our volunteers who aren't currently taking units. However, for our team, we have a total of 70 units being taken right now, which corresponds to 1,140 hours of work for weeks 1 through 6. This is our project timeline. Right now, we are awaiting SpaceX feedback of our preliminary design brief, which was submitted earlier this month. In the winter quarter, we will begin component testing and subsystem integration, which will carry on into spring quarter, and we will submit our safety package, which is a required SpaceX document. Near the end of spring quarter, we'll begin our full systems testing, which will go on throughout the summer until our competition date, which has yet to be announced. And our total budget for our project is $84,369.48. Fortunately, 41.3% of this has been covered by donations from the previous team, and the rest of it will be covered by in-kind sponsorships from our sponsors and our ZOP vendor campaign. And the pie chart to the left shows our costs broken down by each subsystem, and this pie chart right here shows our funding plan broken down by each form of funding. Any questions?
All right, so I really love the graph.